So I want to switch gears a little bit and talk about the potential for number of stereoisomers for a particular configuration. So let's take a step back and consider a molecule that contains multiple stereocenters. If a molecule has one chiral center, we say that there are two enantiomers. One of those enantiomers will be the S configuration, and one will be the R configuration. If a molecule has two chiral centers, we say that there should be four possible stereoisomers. And that word possible is playing a big role here, and we'll talk about that in a second. If a molecule has three chiral centers, the maximum number of stereoisomers that you can have is 8. So again, 8 possible stereoisomers. So you can go on and on and on here, and what it tells you is that the maximum number of stereoisomers for a particular constitution, a particular set of atoms arranged in a certain way, is equal to 2 to the n, where n is the number of chiral centers. Have to proceed with caution, however, because some stereoisomers in the total possible number, some of those stereoisomers may be meso and therefore identical to some of the others. And this will reduce the overall number of stereocenters by a couple. So let's talk about the relationship between these possible stereoisomers. So let's take the example of a molecule that has two chiral non-racemic stereocenters. And I should also indicate that those stereocenters are also non-meso. So two chiral non-racemic, non-meso stereocenters. We know from the equation 2 to the n, that's 2 to the 2, and so we should have 4 possible stereoisomers. All right, so let's draw out an example of that. So let's say we have this molecule here. So we have carboxylic acid, we have an alcohol group that's coming out towards you, another alcohol group coming out towards you. We have two stereocenters here. We have one at that position, and we have another at this position. So I'm going to call it the blue and the red. If you were to assign the absolute configuration of each of those stereocenters, you would get, in the case of the blue, you would get R. In the case of the red, you would get S. Now let's do the case where we have the same configuration, but instead placing those two OH groups with a dash. Again, we have two stereocenters. Nothing has changed there. All that's changed is we've now taken the configuration and made it a dash. And if you were to assign the absolute configuration for each of those stereocenters, you would get S for the blue and R for the red. And if you were to compare these two molecules, you would find that they are non-superimposable mirror images, and so they are enantiomers. Indeed, as you go from the first molecule to the second molecule, you change the configuration at each and every stereocenter. So what was R becomes S, and what was S becomes R. Every single stereocenter changes. All right, so now let's draw a molecule in which we have, let's say, one of the stereocenters is a dash, and one of them is a wedge. So let's do this one where the OH is a wedge on the bottom, and on the top it's a dash. In this case, again, we have two stereocenters, the red and the blue. The blue one is going to have a configuration of S. The red one is going to have a configuration of R. Let's draw the other possibility. The other possibility would be the one in which we have a dash on the bottom and a wedge on the top. Again, two stereocenters, the red and the blue. The blue would be R, and the red would be R. Excuse me. Go back, I made a mistake. Over here on the left-hand side, the red in this case is an S stereocenter. So this was an SS molecule. Now, if we were to compare these two molecules, the one on the bottom left with the one on the bottom right, those are also enantiomers. They are non-superimposable mirror images of one another. And in the case of the absolute configuration, both stereocenters changed. So as you go from left to right, what was an S stereocenter becomes an R stereocenter at both stereocenters, at both chiral centers. But now let's compare up and down, and then diagonal. So these two molecules here on the left, the top left and the bottom left. In this case, the red stereocenter is still S in both cases, but the blue stereocenter changes. In this case, we say that those two molecules are not superimposable and also not mirror images, and so they are diastereomers. And so diastereomers will be a case in which you change every single stereocenter but one as you go from one molecule to the next, or you change none of the stereocenters but one. Whereas in enantiomers, you change all of the stereocenters. Likewise, if you look at the bottom right and the top right, these are also non-superimposable, non-mirror images, and so we call those diastereomers as well. The R configuration on the red carbons stays the same, but the other one changes from S to R or R to S. And so this is all but one, or only one. And then if we compare the top left to the bottom right, now the blue stereocenter stays the same, but the red one changes. And so this is also a case in which we have a diastereomer, set of diastereomers. And if we compare the top right to the bottom left, the S stereocenter stays the same, the blue one, but the red one changes. And so again, this is an example of a diastereomer. It's a non-superimposable, non-mirror images. Okay, so this diagram tells us that when you're comparing stereoisomers, if one stereocenter changes R or S designation and the others stay the same, they're diastereomers. If all of them change except for one, they're still diastereomers. But in order for them to be enantiomers, all of the stereocenters must change their configuration.